All right, today we're going to tackle a classic coding puzzle that looks so simple on the surface. You see it everywhere, coding interviews, online challenges, you name it. But hiding just beneath that simple exterior is a really clever trap that I've seen catch even really good developers off guard. So let's dive in and break it down. So let's just jump right in with a question to get you thinking. If I give you the number 123, how would you go about flipping its digits? Yeah, 321. It feels totally obvious, doesn't it? But as we're about to find out, in the world of programming, sometimes the most obvious path leads you straight into a hidden pitfall. Okay, so let's actually build out that simple reversal first. We'll get the basic logic down, but just keep that little question simmering in the back of your mind. What could possibly go wrong here? Okay, so here's the official problem statement you'd see on a coding site. We're given a signed 32-bit integer, which just means it can be positive or negative, and it has to fit within a specific size limit. Our job is to reverse the digits. But here's the kicker, the rule that changes everything. If reversing the number makes it too big to fit in that 32-bit space, if it overflows, we have to return 0 instead. This one little rule is the key to the whole puzzle. Now, you might be thinking, why not just turn it into a string, reverse it, and call it a day? And yeah, for some problems, that's a great approach. But we're going to solve this the mathematical way. We're going to use a pretty neat trick to peel off each digit one by one, like we're taking apart a little machine. So our whole game plan boils down to this little 4-step loop. We're going to pop off the last digit, push it onto our running total, and then chop that last digit off the original number. And we just keep doing that over and over again until the original number is all gone. All right, let's walk through this with our example, 1, 2, 3. We're going to keep an eye on 3 variables here. X is our input, remainder is the digit we managed to pop off, and result is where we'll build our final answer. And notice, result starts at 0. First things first, we need to grab that last digit, the 3, and the perfect tool for the job, the modulo operator. 123 modulo 10 basically asks, what's the remainder when you divide 123 by 10? Well, the answer is exactly 3. Okay, let's update our little scorecard here. Our remainder is now 3. To build the result, we take what we have so far, which is 0, multiply it by 10, and then just add our remainder. Boom, we have 3. And finally, to get rid of that last digit from x, we use integer division. 123 divided by 10 just gives us 12. And just like that, one cycle is done. All right, round 2. Our x is now 12, and our result is 3. We're just going to run the exact same play again. We take 12 modulo 10 to pop off the next digit, which is, of course, 2. And this is where you can really see the magic happening. Check this out. We take our old result, 3, and multiply it by 10. That kind of scoots it over 1 decimal place to make it 30, right? Then we add our new remainder, 2, and bam, we get 32. Meanwhile, our x gets divided by 10 and becomes just 1. Okay, home stretch, x is down to just a single digit, 1. So 1 modulo 10 is just 1. We've got our last digit, and we're ready to finish this thing. And here's the final piece of the puzzle. We take our current result of 32, multiply it by 10 to get 320, and add that last remainder of 1. The grand total is 321. Now, when we divide x by 10 one last time, it becomes 0. That's our signal to stop the loop. And look at that. Our result is 321. Perfect. For this number, our logic works like a charm. So everything seems fine and dandy, right? The logic is solid. But now we have to face the music. We have to deal with that little constraint we talked about at the start. This, right here, is where our simple problem turns into a real head-scratcher. Okay, so a 32-bit signed integer has a maximum value of about 2.1 billion. Think of it like a bucket. It's a really big bucket, but it can only hold so much. If you try to pour in even 1 drop more, it overflows. In programming, this is called an integer overflow, and it can cause all sorts of chaos. So what do you think happens if we feed our perfect logic a number like this one? Now, on the surface, it's a totally valid number. It fits in the bucket just fine. But take a look at that last digit, a 9. Remember, that's going to become the first digit of our reverse number. And overflow. When we reverse it, we get a number over 9.6 billion. That's not just over the limit, it's way over. It completely shatters our 2.1 billion ceiling. At this point, our program would either just crash, or even worse, it might silently store some totally bizarre garbage number. Our beautiful logic has completely failed us. So how on earth do we fix this?
The rules of the game say we can't just cheat and use a bigger bucket, like a 64-bit integer. That means we have to be smart. We need a way to see the disaster coming before it actually happens.
And the solution is it's really elegant. We know the exact moment of danger is when we multiply our result by 10. So the trick is to check something before we do that multiplication. If our current result is already bigger than the maximum possible integer divided by 10, then we know for a fact that the next multiplication is going to send us over the edge. It's like a preemptive strike. Okay, let's put this to the test with our problem number. On the left, you've got our old, naive code. On the right, our new, smarter code. Right before that final step, our result is over 964 million. The old code just blindly multiplies by 10 and boom, disaster. But our new code, it pauses. It asks a simple question. Hey, is 964 million bigger than the max limit divided by 10? And since the answer is yes, it is, we just stop right there. We return 0, just like the problem asked us to. No overflow, no crash. Problem solved. So now that we have this awesome little safety check in our back pocket, we can put together the complete, bulletproof solution that handles everything. So here it is, the whole shebang. First, you deal with the negative sign. Just put it aside for a second and work with the positive version of the number. Then you start your loop. But, and this is the most important part, you perform that overflow check before you multiply. If you pass the check, you carry on, calculate your remainder, build your new result. Once the loop is done, you just slap that negative sign back on if you need to. That's it. This thing will handle every single case you can throw at it.
So what are the big takeaways here? Well, first, we learned a really cool mathematical trick to pull numbers apart using modulo and division. But I think the bigger lesson is that in these kinds of puzzles, the constraints, they're usually the real problem you need to solve. And the most elegant solution is all about checking for that overflow before it can ever happen. It just goes to show you that even the simplest problems can hide some really deep complexity.
You know, this whole problem looked so straightforward at first, but it was hiding this really deep logical trap. It just makes you wonder, right? What other simple problems out there are just waiting to surprise us with a hidden twist? So yeah, keep questioning and keep exploring.